Okay, this is a quick introduction, kind of motivation for using f-test to select regressions. So what we're trying to do here is we have some data. Remember from the previous lecture we had income and test scores, and that data looks something like, if we plotted it, looks something like that. And so we want to test different functions, functional forms. Remember we were talking about the f of x's. We want to figure out what's the best functional form for our data. Is it a linear model? Is it a quadratic? Is it a cubic? Or maybe even a logged functional form. So we're going to get now into, we're going into testing different models. We can use F statistics to do that. And so here we can use the F test from the previous lectures or T test to test the null hypothesis of linearity. In other words, we can test the functional form against alternatives that the population regression is quadratic or cubic. So now we're almost specifying hypotheses about the functional form of the model. Well, actually, we aren't almost doing that, we are doing that. If only quadratic, we can use the t-test to test the coefficient on income squared. In other words, if we're only estimating the model that I've written down here, we want to test it against a linear model. All we have to do is the regular t-test on beta 2 to tell us if beta 2 is different from 0. If it's different from 0, then it's probably safe to assume we should have the squared term in there. If it's not different from 0, if we fail to reject or null that it's different from 0, then we can conclude that the linear model is sufficient for our data. If a cubic, then we need an f-test. So let's look at that. So suppose we have a cubic regression. Now we have test scores on income plus income squared plus income cubed. The null hypothesis that the regression is non-cubic is that we're going to specify this null, h naught, as beta 2 is equal to beta 3, which is equal to 0. So the null hypothesis is that this whole bit right here doesn't matter. Versus the alternative that one or the other or both of those variables matters and the coefficients are non-zero. It turns out in large samples, remember we've seen this before, that assuming the t-stats of each of the variables are not correlated, this implies that the f-stat or the f-statistic has a chi-squared distribution with q degrees of freedom, and the f-statistic itself is the chi-squared critical value divided by q. So let's go to the chi-squared table, look up the value and divide by q, and this will be a rejection level. So what's our q here? We have 1, 2 restrictions. So q is going to be equal to 2. In this example, the f-stat produces, or the f-stat is the following, 37.69. So we're going to need to figure out our critical value here on the next slide. So we're going to be using the 5% significance level. That's this thing here. With 2 degrees of freedom. So we take that row out to that column and we get 5.991. Okay, so for q equals 2, the critical value is 5.991. We're going to divide that by 2 because of what we said in this slide here. The f-stat is distributed chi-squared with q degrees of freedom divided by q. So that's roughly equal to 3, so our critical value is roughly 3. And remember the f-stat in this example is 37.69, so our rejection rule, reject if f-stat is greater than the critical value. So I'm not giving you 1.96 or some value at this point, because really this critical value depends on the number of restrictions we have. So it's going to depend on how many coefficients you're testing. So in this case it's 3. Our f-stat is 37.69. So is that greater than 3? Yes. So we reject at least a 95% confidence level, but in this case it's pretty safe to assume that we're rejecting at the 1% confidence level. We can actually go back and figure that out. We can say, oh, here's our 1% significance level. We have 2 degrees of freedom. So we're going to take 9.2 divided by 2. What does that get you? 4.6. Okay, so that's just an introduction to the f-stat for selecting between models. I forgot to tell you, okay, so we've rejected the null hypothesis here. What does that mean? That means going back to our original model, that means these two coefficients, the beta 2s and beta 3, those are, we can reject the null hypothesis that those are 0, and so we now reject the linear model, and we say that the cubic is a better fit of the data, at least to the linear, but we haven't gotten to testing the cubic versus the quadratic.